Hi, so I wanted to do a quick walkthrough of the exercise, the optional exercise I had posted for Wednesday. So I am going to walk through this. So hopefully you've already had the opportunity to try some of these on your own. And if you haven't, maybe pause the video now and take a stab at working through some of these problems. And if you run into trouble, play some of the video, figure out what I'm doing, and then pause it again and keep going forward from there. Okay, so here we have a converging mirror and an object that's placed about 2.2 meters away from that converging mirror. And the converging mirror has a focal length of 90 centimeters, or 0.9 meters. So first we want to figure out where is the image going to form and kind of classify what's it going to look like in terms of magnification and about where does it form and things like that. So to do that, I'm going to draw in the principal rays. So I'm just using this here as a straight edge to draw in right now. The first principal ray I'm going to draw is parallel to the optical axis, and since this is a converging mirror, it will bounce off towards then the focus. So there's my first of my principal rays. I also know I should be able to form a ray that goes through the focus and then bounces off parallel to the optical axis. So I'll draw that one as well, like so. So that's already enough to maybe give us a good guess at where this image should form, but just to finish this off, we can come in and have a ray that goes and meets the mirror at its center and then leaves with the same angle that it comes in, something like this. And there we go. We see all three of those rays meet at the same point, and so we can draw in our image just like that. So now we know that this image should be inverted, and it should be somewhere between the focus and the object, and we could probably, we could use this ruler here to measure exactly where we think that might be, but to be more exact, we would want to calculate this with our thin lens small mirror formula, like so. And in this case, since this is a mirror, the image forming on the same side of the mirror means a positive image distance. And since we have a converging mirror, we're also going to have a positive focal length. So in fact, all of our distances will be positive in this formula. So let's plug some of those numbers that we know in this case, the focal length being 0.9 meters. Our object distance is 2.2 meters. So the only thing we don't know is the image distance here. And so now what I can do here is maybe just move this 1 over 2.2 to the other side and see 1 over the image distance is 1 over 0.9 minus 1 over 2.2. I just subtracted 1 over 2.2 from both sides. And if I plug those numbers in to my calculator, I would get 1.11 repeating minus 1 over 2.2 is 0.454, so on. And if I subtract those numbers, my answer for 1 over the image distance is 0.66. Rounding up to 0.66. So then the image distance is just 1 over that number, which is 1.52 meters. So that's the first thing that we needed to find. The second thing we want to find is the magnification, and we needed to find this to get there in the first place. So now we know the magnification is minus the image distance over the object distance, so minus 1.52 over 2.2, or minus 0.69. And of course, we knew it was inverted already. We also probably could have figured out that it's a bit smaller. The image I drew here is smaller than the object. So it is in between -1 and 0, as we might have expected, and it's 1.52 meters away from the mirror. Here the mirror is at about 2.2 meters, so going 1 meter back would be here, and then 1, 2, 3, 4, 5, 50 centimeters back. So yeah, about 1.5 meters back from the mirror. So that all checks out. Okay, so the second one down here we can take a look at. Now instead of a converging mirror that we had here, we're going to have a diverging lens. So we have now our object is about now 90 centimeters away from the lens. Focal length is a little bit closer, about 80 centimeters away. And in this case, we could again go and start drawing our principal rays. So here I'm going to draw in the principal ray that's going to go in like this. Now I'm just assuming that this, well, so maybe I should continue drawing this lens as though it were a bit bigger than how the image here shows it, because I'm going to assume it's still large enough that this ray is going to hit the lens and refract. In this case, we know it's going to diverge away from this focus, so it's going to do something like that. And of course, maybe what I should do here while I have this is draw in the direction that it looks like that ray is coming, in case that becomes relevant. Then we can, of course, draw in a ray that's going to go to the center of our optical object and just pass straight on through. It's not going to change direction at all. And then lastly, I can draw a ray that is going to, on the object side, pass moving in the direction that would hit this focus over here, and then it should leave parallel to the optical axis. Now, the way to understand this is that over here, if we thought about a ray originating, let's see here, a ray coming into the lens parallel to the axis, looks like it's diverging away. So here, now you'd say, okay, well, if this one was coming this direction through parallel to the optical axis on this side, it would diverge away from this point. So we can understand that ray in that way. Of course, I'm going to then make this a dotted line going this way here, and see that all three of these rays, which are diverging on this side, would have converged on this side. So this is where the image is going to form. In this case, this is a virtual image, whereas one we saw above was a real image. But the light rays don't all actually converge at the image here, because these two that are projected backwards, that light never actually meets at that location. So this is a virtual image. It is upright and it is smaller. So we would expect some magnification between 0 and +1. But to figure out this exact image distance here, again, we're going to use this formula. So here, our image distance is likely will be negative because it's a lens and it's forming on the same side of the lens as the object. But we'll also have a negative focal length because we have a diverging optical object here, our optical device. So when I plug this into the formula here, for this 0.8 comes along with a minus sign because it is a diverging lens. The object distance is +0.9, and then we would solve for the image distance as we did before. So again, what I can do is move this 1 over 0.9 over to the other side and see -1 over 0.9 minus 1 over 0.8 equals 1 over di. And then I can plug these into my calculator and say 1 over 0.9. Well, we did that before. That's about, in this case, minus 1.11. And then 1 over 0.8 is minus 1.25. Is 1 over di. And that, if we finish subtracting those numbers together, gives us about minus, I'll say 2.4-ish is my 1 over di. And that will give us, if I invert both sides of that, minus 0.42 meters for our image distance. And of course we could double check this here. Our lens is at about 100 centimeters, so we would have to go back about 60. Yeah, so we're at about 58 centimeters where that image formed. So that matches up very well. Okay, then we would finish off by calculating the magnification and say that is minus di over do, and that's minus negative 0.42 over 0.9, and that would give us about positive 0.47. So we should have about, it should be upright because it's positive, and it should be about half as big. And that matches up pretty well with what we saw here. Okay, so that's a converging mirror and a diverging lens. Lastly, on the other side, we can take a look at some of these kind of optics of the eye problems that we were looking at and say, well, if we're farsighted, that means we, our patient is farsighted, that person cannot see clearly when the object is very close up. So that's when the eye is pulling the most on that, or the muscles in the eye are pulling the most at on the lens and making it kind of the roundest it can be, fully accommodated, is how we would say that, maximum optical power that the lens can produce. So that means, since we can't see when we're at that point, that means our lens is ending up too weak. It's under converging these rays. So we need to add a converging lens in here. So A would be a converging lens is what would be required to help our patient better see, because we want to make sure that these rays meet up properly to form an image at the retina, not behind the retina, which is kind of what's happening currently in their eye. Okay, so then we want to figure out, okay, what would the distance to the lens, distance from the lens to the object that they want to be able to see. In this case, they want to be able to see something at about a distance of about 20 centimeters from their eye. So in this case, here I could draw a little drawing. Here's my patient's eye, and here's where that converging lens that we're going to put in front of their eye to help them see better. And here I'll draw in, this is their goal. This is 20 centimeters from their eye. But the glasses are going to sit a little bit in front of their face. Xi, in this case, is 1.6 centimeters. And so the object distance is where we're going to put, say, like a book, something here. I'll write book. This is where they want to be able to read from this distance. They're going to hold the book here, and so that's going to be the object for our lens. We're going to want to create an image further away so that the patient will be able to read it based on using that image to create the image that forms within their eye. So the image that forms from the lens will be the object for their eye. So this is going to be our object distance. So in this case, we could say the goal, which is 20, I'll convert everything to meters, so 0.2 meters, in this case, is going to be our total, and that's going to be equal to dO plus xi, which is this 0.016 meters, or 1.6 centimeters. So then dO in this case is going to be 0.2 minus this 0.16, so that's 0.184 meters for the object distance relative to the location of the lens. So that's going to be what's important for finding the optical power of the lens. Okay, so now C, we want to then think about the distance to the image that should be formed by the lens. Now this is going to be formed at the patient's near point. So if somewhere far out here, say, I'll draw in this, and this is again relative to the eye position, this is their near point. This is the closest location that they are able to see clearly, because they can see far away. When they bring it closer and closer, there's some position where it stops being clear. That's right here. This is where we want to form that image at the near point. So I'll write near point here. So then I can also draw in, well, if this is where that image is going to form, the image distance relative to the lens is going to be this length. And so now the near point, which is what, 1.4 meters for the near point, is going to be equal to the image distance plus, again, that xi, which is image distance plus 0.016 meters again. So we would subtract 0.016 from both sides and get 1.384 for the image distance. But here we have to be careful because the image is on the same side of the lens as the object. So we actually have to make this negative to correctly account for the signs here. And then lastly, if we plug all of this into our formula, we would say that the power of our lens should be, well, it's 1 over f, which is 1 over the image distance plus 1 over the object distance. If we plug in those numbers, we'd get 1 over minus 0.384 plus 1 over 0.184, which is minus 0.72 plus 5.43. And lastly, adding those numbers together, we get about 4.71 diopters for the optical power. And this optical power is positive because it's a converging lens that we're putting in front. And yeah, this is what we should prescribe to our patient. Okay, so hopefully that helped. And if you have any questions about any part of this exercise, please send me an email or come talk to me in office hours on Friday or something. Otherwise, I hope you have a great rest of your day, and I'll see you later. Bye.